Hi, I am Massimo Banzi and I like to make things. And welcome to another Arduino tutorial video. Today we're going to be building a theremin. The theremin is a musical instrument that produces different sounds depending on the position of the hands of the player around the instrument. In this particular case, we're going to be building a very simple theremin using a light sensor as a way to capture the position of the hand of the player from the Arduino. You'll be using a photoresistor to detect the amount of light, and from the amount of light we are going to guess the distance of the player's hand from the sensor. So here we have a piezo buzzer. The piezo buzzer produces sounds every time it's turned on and off. It's connected with the wire to pin number 8. While here we have a light sensor connected to analog input 0. So the light sensor detects the amount of light that hits the surface of the sensor. So by moving the hand from the sensor, we reduce or increase the amount of light that hits the sensor, and in turn, this information goes into the Arduino as a variation of voltage. In our code, we're going to use the variation of voltage to gauge the distance of the player's hand from the sensor, and we're going to map that to the appropriate values of sounds, and then we're going to drive the piezo capsule using the tone function in Arduino. Let's start building the circuit. The first thing to do is to connect the power bus with a red and black wire to the two strips on the side of the breadboard. Then we connect the piezo buzzer. Since the piezo buzzer is a bit tricky to mount, we have to prepare the two wires at the right distance on the breadboard and then plug in the piezo in the correct lines on the breadboard. Now let's place the photoresistor. Here is the photoresistor. We place it on the breadboard. We connect a resistor between this leg of the photoresistor and ground. Then we have another wire going from the 5-volt rail to the other side of the photoresistor. And then one wire connects the photoresistor and the resistor here to the analog input 0 of the Arduino. So in this case, we have set up a sensor that reads the amount of light and converts that into voltage that we can measure with Arduino. And then we have connected an actuator, the piezo capsule, that produces sounds. And now we're going to write a piece of software that ties them together. The software that we're going to be using with this project starts off with a 5-second calibration period. So during this time, you will move your hand near the sensor like this to let the Arduino calibrate the values that represent the minimum and the maximum amount of light that can hit the sensor. After those 5 seconds, Arduino will start the main loop. And during the main loop, we have a very simple structure. We read the amount of light in terms of voltage applied to the analog in, and then we convert that to a suitable frequency to play on the piezo speaker. And then we use the tone function in order to play that sound. Let's look at the code. We start off at the beginning defining a few variables. The first one is called sensor value. It's an integer variable that stores the values read from the light sensor. After that, we define two variables called sensor low and sensor high, and these are used in the calibration phase to determine which one was the minimum and the maximum value read from the sensor. So where's the trick? As you can see, we are defining the variables. Sensor low starts off as 1023, and sensor high starts off with 0. This is done on purpose to make sure that if we read a value from the sensor it will always be less than 1023. So if we start with sensor low at 1023, we make sure that the first value that we read will be less and the calibration can operate correctly. At the same time, we are using sensor high and setting it up at 0 so that any value that we read from the sensor will hopefully be more than 0. After these variables, we define the classic constant LED pin, and we assign 13 because we're going to use the LED to signal when the calibration phase is over. In the setup, we have pin mode, defining pin number 13 as an output. And then we digital write onto LED pin high, so we basically turn on the LED to signal that the calibration phase has begun. Then here, we have an interesting piece of code. It's a while loop that uses the millis function to make sure that the calibration phase lasts for exactly 5 seconds. So how's that done? So the millis function is a function that returns the number of milliseconds that have passed since the last time that the Arduino board was turned on or reset. So every time you upload code, or you press the reset button, or you plug the power, the Arduino starts from 0 milliseconds, and millis will return a number that grows as time goes by. What we're going to do here is that since this code is exactly at the beginning of the setup, it's happening in a very few milliseconds right after the board was turned on. So by doing while millis less than 5,000 that we have here in the while loop, we make sure that the code within the while loop is executed only during the first 5 seconds that the board has been turned on or reset. So what is happening here? So we read, through analog read, we read input 0, we place that into sensor value, and then with a very simple algorithm, we check if sensor value is more than sensor high, then we make sensor high equal to sensor value. So essentially, we are saying, is the value that I'm reading from the sensor right now higher than the highest value I have read until now? If that's the case, then that value becomes the highest value that we have read until now. The same thing we do for sensor value and sensor low. So again, we check if sensor value is less than sensor low, then sensor low becomes equal to sensor value. This code gets executed as many times as possible within the 5 seconds after the board was turned on or reset. So if I move my hand on the sensor like this during the first 5 seconds that the program has started, I basically let the light sensor experience all the possible values of minimum and maximum light. And after that, I come out of this calibration phase with the maximum and the minimum values stored in sensor low and sensor high. Then you can see here with digital write LED pin low, we are turning off the LED to signal that the calibration phase is over. And then the loop is very simple. During the loop, we read the analog input 0 and we store that into sensor value. Then we are going to use an interesting function called map, because we have a minimum and a maximum value that the sensor can read in the current light conditions. And then we have the minimum and maximum audio frequency that we want to play back. So instead of having to calculate manually the matching between those values and the frequency value that we want to play back on the piezo speaker, then what we're going to do, we're going to use this function called map. Map is very simple to use. We specify a value that we want to map. The first parameter is sensor value. Then 2 parameters follow sensor value. They determine which is the value range that the input value can have. So sensor low and sensor high determine, this is the range of values that sensor value can assume. The last two parameters of the map function, they determine which is the output range that we expect from map. So very simply we say, this is a value. This value can be between a minimum and a maximum value, and depending on which value I am processing, I want to produce a value which is within this other range. So our aim is to basically say, for any value within sensor low and sensor high, we have to produce a number between 50 and 4,000 that represents the frequency of the audio signal we want to produce. The result of this calculation goes into the pitch variable. In the next line of code, you can see that tone is producing a sound on the piezo speaker connected to pin number 8, and the pitch is the value that we calculated previously using map, and then 20 is the duration of this sound. After this sound has been produced, we delay for 10 milliseconds, and then we continue. So now let's upload the code onto the board and see what happens. You can see that if you gauge your movement properly, you can produce a lot of different sounds. I'm sure you will find this project funny, probably for the first 5 minutes. Then the sound will become too annoying and you will be prompted to do this. So thank you for listening. So now you have to build it, hack it, and share it, because remember that Arduino is you.